Hello everyone, my name is Pranshu Dhumra. Today I am here to present my task 8.1 HD, which is mainly based on Bluetooth communication between embedded devices. Like there are in this project, I have made a reverse parking systems for car garage. The system consists of two main units, a sensing unit that detects how close the car is to the wall, and an actuating unit that sends signal to the sensing unit where it alerts the driver. These two subsystems communicate wirelessly using Bluetooth Low Energy Protocol, that is BLE. The sensing subsystem uses an Arduino Nano 33 IoT with a light sensor mounted on the wall, while the actuating unit that is Raspberry Pi and with the LED inside the car. As the car approaches the wall, the light intensity of the backlight increases, triggering the LED to turn on and warn the driver. Now explaining you the hardware architecture. First, the sensing unit consists of Arduino Nano 33 IoT and BH1750 digital light sensor, which is this. So the BH1750 is a high precision ambient light sensor that measures the illumination in lux units. It communicates using two wires, that is SDA for data and SCL for clock. The wiring is simple. The BH1750's VCC connects to the Arduino's 3.3 volt power pin, and GND connects to the ground of Arduino Nano, and SDA to the Arduino's SDA pin, and SCL to the Arduino's SCL pin. The I2C protocol here allows multiple sensors to share the same route, making it very efficient. Now coming on to the actuating system, which is Raspberry Pi. As you can see, this is the hardware. Here an LED is connected to GPIO pin 17 through a current limiting resistor of around 220 to 330 ohms to protect the LED. Now the LED's anode connects to GPIO 17 through the resistor, and cathode connects to the ground. For the communication, we use the two devices communicate using Bluetooth Low Energy, that is BLE, specifically for GATT protocol. That's generic attribute profile. BLE is ideal for this application because it consumes very little power compared to classic Bluetooth, and it's perfect for transmitting small amount of data frequency like sensor readings. Now coming on to the libraries. For Arduino Nano 33 IoT, I am using three main libraries. First is wire library, second is BH1750 library, and the third is Arduino BLE library. First, the wire library in Arduino's is the standard library for I2C communication. It handles all the low level communication protocol with the BH1750 sensor. Secondly, the BH1750 library provides high level functions to easily read light values from the sensor without worrying about the sensor's internal registers and commands. Now the third one, that is Arduino BLE library. This is specifically designed for Arduino Nano 33 IoT on board Nina B306 Bluetooth module. It provides simple functions to create BLE service and its characteristics, advertise the device, and send notification to connected clients. And for coming on to the libraries used in the Python code, that is for Raspberry Pi. I first used rpi.gpio as GPIO, as you can see. This is a standard library for controlling Raspberry Pi's GPIO pins. I use it to turn LED on and off. Then I have used async IO library. This is Python's library for asynchronous programming. BLE operations are asynchronous, which means that program can do other things while waiting for Bluetooth data, making the system more responsive. Then the third is Bleak import, which is import from the Bleak scanner and Bleak client. This stands for Bluetooth Low Energy Platform Agnostic Client. It's a modern Python library that makes it easy to scan for BLE devices connect to them and receive notifications when data changes. Now the communication process used in Bluetooth is the first step is the Arduino advertising. When the Arduino starts up, it configures itself as a BLE peripheral device. It sets its local name to BH1750 sensor so it can be easily identified during scanning. The Arduino creates a custom BLE service with a unique UUID, that is universally unique identifier, which acts like an address for the service. Within this service, it creates a characteristic for the Lux data with another unique UUID. The Arduino starts advertising, essentially broadcasting its presence and saying, "I am here, I have light sensor data available." Now, then the further step comes is Raspberry Pi scanning. On the Raspberry Pi side, my Python program starts scanning for nearby BLE devices. It specially looks for a device with the name of BH1750 sensor, and the scanning process listens for advertising packets for nearby BLE devices. Now then comes the connection establishment. Once the Pi finds the Arduino, it initiates a connection request. The Arduino accepts this connection and they establish a secure BLE link. This process is called pairing in the GATT protocol. Then for the notification subscription, after connecting, the Raspberry Pi subscribes to the notification from Lux characteristics. This means that whenever the Arduino updates the Lux value, it will automatically notify the Raspberry Pi without the Pi having a constantly ask for updates. This is more efficient than polling. Now explaining the Arduino.iono code. First, the program begins with the setup function, which runs once when the Arduino powers on. First, it initializes the serial communication at 115200 baud rate for debugging purposes, and then it initializes the I2C protocol, which bus by calling wire.begin, which configures the SDA and SCL pins for communication. Next, it initializes the BH1750 sensor in continuous high resolution mode. This mode means that the sensor continuously takes the measurements with 1 lux resolution, providing approximate readings. If the sensor initialization fails, maybe due to loose wiring, the program enters an infinite loop to prevent further execution. After the sensor is ready, the code initializes the BLE module, where it sets the local name to BH1750 sensor and create the BLE service and characteristics with their respective UUIDs. The characteristic is configured with two properties: BLE read, which allows the Raspberry Pi to read the current value, and BLE notify, which allows the Arduino to push update automatically. The characteristic can hold up to 20 byte of data, which is plenty of a numeric lux value. Finally, the Arduino starts advertising and waits for the connection. Now in the loop function, the loop function runs continuously after setup completes. First, it checks if any central device, that is BLE terminology for a client like a Raspberry Pi, has connected. If no device is connected, it simply keeps the BLE stack running by calling ble.poll and continues advertising. Then when the Raspberry Pi connects, the Arduino enters a while loop where it runs as long as the connection remains active. Inside the loop, it reads the current light level from the BH1750 sensor using read light level function, which returns the value as a floating point number in lux units. The code includes the errors checking. If the sensor returns NaN, means not a number, it indicates a sensor reading error. If reading is valid, the code converts to the float to an unsigned long integer by adding 0.5 to proper rounding. This integer is then converted to string and being stored in a character buffer. Now the code uses luxchar, which is the most important part. Luxchar.write value to update the characteristic with the new lux value, because the characteristic has the BLE notify property enabled, and this automatically triggers a notification to be sent to Raspberry Pi if it's subscribed. This happens every 500 milliseconds, providing twice per second updates. The BLE.poll function is called regularly to keep the Bluetooth stack processing incoming and outgoing messages smoothly. Now coming on to the Python code. At the top of the code, I define several important constants, which is define a device underscore name, which is set for BH1750 sensor to match the Arduino's advertised name. Char underscore UUID is the exact same UUID used in the Arduino code for the lux characteristics. These must match perfectly for communication to work. Now then, the pin is defined to 17, which corresponds to GPIO 17 on Raspberry Pi. Then the threshold is set to 50 lux. When the light level drops below this value, we consider it too dark and LED will remain off. Then I configured the GPIO library using BCM mode, which means I am referring to pins by this Broadcom GPIO numbers. Then coming on to the notification handler, the handle underscore notification function is callback function. It gets called automatically whenever the Arduino sends new data. It receives two parameters: sender, which identifies which characteristic sent the data, and the data, which contains the actual byte sent by the Arduino. Inside it, the code first decodes the bytes into string, then strips any white space, then converts it into an integer lux value. After successfully decoding the lux value, it prints value for monitoring. Then comes the decision logic. If the lux value is below threshold, that is, it means the environment is dark, so the LED will remain off by setting GPIO 17 to low. If the lux becomes above the threshold, the environment is bright enough, so the LED is turned on by setting GPIO 17 to high. This is the reverse parking scenario, where a certain light indicates the car is too close to the wall. Then the main function, which is async function, which is the asynchronized part. This is an asynchronous function that handles the Bluetooth connection process. It starts by scanning a BLE devices using bleak scanner dot find underscore device underscore name, looking specifically for BH1750 sensor with 10-second timeout. If no device is found within this time, the program prints an error and exits. And once the device is found, the code uses an async context manager to establish connection with bleak client. This is the programming practice that we use because it ensures the connection is properly closed even if an error occurs. After connecting it successfully, the code calls start underscore notify, passing the characteristic UUID and the callback function. This subscribes to notifications from the characteristics. Now the main execution part here is the block which uses asyncio.run to start the asynchronous run function. This is the block for proper resource management. If the user presses Ctrl C to stop the program, the keyboard interrupt exception is caught gracefully. The finally block ensures GPIO.cleanup is always called, which resets all GPIO pins to their default state and prevents the warning on the next run. Now I will show you the system testing and proper working of the hardware setup. Now I will show the output for this task. So first we'll upload the code. After compiling, the code will be uploaded. Now we can see our sensor is ready and we have started the advertising of our device. Now we'll move to a terminal which is on VNC, and we'll upload the code. Code here. Now we can see that it is scanning for device and it has found the device connected with the sensor. As we can see, initially the lux value is very low, as the car will move towards the wall and it will show a sudden change. We can see here the light is very bright and the lux value immediately increases and the LED turns on. Then again, when lux value is decreased, the LED turns off. So the logic behind it is that it will, when the car will move towards the wall and it will sense some sort of light of the car, it will give an signal to the LED connected, and it will start blinking. Thank you so much.